Hello, welcome to the course Electronic System Design. Last lectures we were discussing about some electrical components, for example R and L, C. These are lumped components which we have talked about, and then we talked about the MOSFET, which is a switch, and this is a semiconductor based devices. MOSFET and BJT, these are active devices where we can expect some gain coming out of the device. However, RLC, these are passive components. There cannot be a gain. There may be a zero loss or practically some loss incurred into the device. So, to make a fruitful system, for example, any electronic system we want to make, we need to take these components together and connect them through wires to make some circuits which is performing certain function. So, today we are going to discuss what do we do with these components and how do we solve when we connect these components together, and how do we come up with the output of that certain circuit. So, today we are going to discuss something called circuit simulations, or the how to solve the circuits in SPICE or any software program, or even by pen and paper. So, today we discuss circuit simulations. So, for a circuit simulation, we have something called a CAD tool, which is called SPICE, or the simulation program for solving these circuits. So, this program, for example, this is that software program. We need to provide two things to this circuit simulator. One is the input and setup. One is the input and second is the setup. Setup means what we want to perform on this schematic or the input circuit. So, this is one thing which goes into the simulator, and the second thing which goes into the simulator is the model of devices. These two things goes into the SPICE program, or it can be any program, or we can say the numerical solver in generalized form. This can be any solver where we perform formulation of circuit equations. And we do solving of ordinary differential equations. Ordinary differential equations, or ODEs. We do some solution of nonlinear equations. We also perform solution of linear equations, and after solving all these things, this numerical solver generates the output, and this output is generally in terms of voltage and currents. So here we see we have a numerical solver. For example, SPICE is a circuit solver. We provide two inputs to this solver. First is the schematic or the circuit diagram, where we specify that these are all the components which we are going to use in our circuit and how they are connected from each other through a resistance-less wire. We most of the time we assume wire is does not have any resistance. This is the schematic, we call it, and then we perform certain function. For example, we apply some type of analysis what we need to perform on that circuit. For example, we want to know the time response of the circuit. If we apply certain input signal, for example a sine wave or square wave, how the circuit is going to perform with respect to this sine wave as an input. So this is the information we feed to this numerical solver. Along with this, we have one more important thing, which is the model of these devices. For example, this resistance, what is the characteristic of this resistance? The resistance is simply not a resistance. It has certain resistance, however, it has multiple other parameters. For example, this may not be a very linear resistance. Along, if we apply the voltage, small voltage, resistance is something. If we apply a very high voltage, resistance may deviate from a linear curve. Similarly, MOSFET is not a linear device. This has a IDVD characteristic, as we saw last time. So those equations or the set of equations is called the model for these devices. So all those devices what we are using in our circuit, we have to specify the model of all these devices. So all these things comes together and goes into a numerical solver such as SPICE. What numerical solver does, it formulate the circuit equations. So we specify the schematic, which is a geometrical connection of these devices, and what this SPICE solver does, it creates the circuit equations based on this schematic. So there are many functions it performs which we are going to discuss today, and then it solves those equations what we perform in this formulation. After solving the equations, we get nodal voltage and nodal currents. So all these variables produce as a output of this SPICE solver. So this SPICE solver generates that output depending upon what model we choose, what elements we are using, how they are connected, and what is the set of function we are performing. Is a transient simulation, or is a DC simulation, or is a operating point analysis. What type of analysis we are doing, based on that the output is generated. So this is how a circuit simulator actually works and produce the output. The very important part in this circuit solver is the formulation of circuit equations. We are specifying connections of the devices, and we need to come up with the circuit equations which we can solve with each other so that we generate the output. So circuit solver also does the same thing, and we can do the same circuit equations we can solve on pen and paper as well. So this is what we are going to discuss now. So we have circuit analysis. So circuit analysis is the electrical circuit elements are idealized models of physical devices that are defined by relationships between their terminal voltages and currents. An electrical circuit is nothing but the connection of circuit elements. Connection of circuit elements into one or more closed loops. Here the basic quantities which we measure are voltage, currents and power. These circuit elements can be passive or active. Can be active or passive. And one of the most important thing is the sign convention. Is important in computing output. So here we have the electrical circuit elements that are idealized model of physical devices. So a model is nothing but the mathematical representation of the device where we assume the device is ideal, or if there are some non-idealities, we try to mimic the behavior of those non-idealities using some mathematical equations which are completely ideal. So that is something called a model of the device, and an electrical circuit is nothing but a connection of multiple such kind of devices. So resistance, capacitance, inductance, transistors, diode, BJT, we have so many components together. If we connect them together through wire, that form something called a circuit. And the basic quantities what we measure in this circuit or electrical circuits are voltage, currents and power. These are the main parameters what we look for in the circuit analysis. These circuit elements can be active as well as passive. We can connect an as active element along with the passive elements, so that a circuit contains mix of both of the type. The very important thing in the circuit analysis is the sign convention. We have to assume certain terminology and we have to stick to that. For example, the flow of current is measured by the movement of positive charge from one side to other side. So the movement of positive charge is considered the direction of current. So if negative charge is flowing, it means the current is flowing in opposite direction. So these are some kind of sign conventions we need to follow to analyze the circuit. So now we have, for example, these devices, independent devices. Let us say a resistance which follows the Ohm's law, V equal to IR. So that itself is not sufficient to completely solve the circuit. So we have certain other rules or the laws developed for circuit analysis. One of them is Kirchhoff's law. So we have two types of laws from Kirchhoff. We have Kirchhoff's voltage law and a Kirchhoff's current law. So these are two types of laws which we are going to discuss. So let us first discuss the Kirchhoff's current law. Or in short, we call it KCL. So this Kirchhoff's current law states that the algebraic sum of currents entering a node an even or a closed boundary is 0. So KCL states that the algebraic sum of current entering a node is 0. So before applying KCL, sign convention is very important. We can follow this sign convention. For example, current entering the node we will consider this negative, and current leaving the node consider it positive. So now if we apply Kirchhoff law to a circuit, so for example we have a node A where we have multiple branches coming in, for example this, this. So this is, let's say, node A, and we have 5 branches connected to this node A. One branch is carrying current towards the node A, I1. I2, let's say, is coming out. I3 is again coming towards node A. I4 is also coming towards node A, and I5 is going away from the node A. So let's say this is the situation. Then the solution of this through this KCL is minus I1 plus I2 minus I3 minus I4 and plus I5. So this is the sum of all the currents coming to the node A, and as per the KCL this sum is 0, or we can say I2 plus I5 is equal to I1 plus I3 plus I4. So here we can see that sum of currents going away from the node is equal to the current coming towards the node. So I2 plus I5 is equal to I1 plus I3 plus I4, or in the mathematical form we can say we have IN, where N is from 1 to capital N. This is equal to 0. So here we have Kirchhoff current law, where this says the algebraic sum of all the currents coming to the node is 0, and before applying KCL we have to follow a certain naming convention. Currents entering the node is considered minus, current leaving the node is considered plus. So if we apply this convention to any of the node, we can write all the sum of all the currents coming towards the node is equal to the sum of currents going away from the node. So this is what the KCL says. So now we see the Kirchhoff voltage law or in short we call it KVL. It says the algebraic sum of all voltages around a closed path is 0. So KVL states that the algebraic sum of all voltages around a closed path or loop is 0. So, for example, we have certain circuit. In this circuit, we have a voltage source which is Vs. This is supplying voltage to resistance R1 and R2. There are two resistances. So, this is a typical circuit what we form using two elements, two passive elements and one voltage source. We can see this is a loop, and if we assume that there is a current flowing in this loop which is I here. So, this current we can assume any direction of this current. For example, in this figure we have seen a clockwise direction of current which is flowing inside this loop. So, we can write from this loop we can write the equation of voltage drop as capital I times R1, which means the voltage across this element, I into R1 plus I into R2, which is the voltage across V2 R2, minus Vs. So, we can see this arrow, this is coming towards the negative terminal of this Vs. So, we will write minus Vs. This is because of the sign convention we use. So, minus Vs is equal to 0. So, this is the algebraic sum of all the voltages in the loop, and the algebraic sum is equal to 0. So, this is the equation what we can write using KVL or the Kirchhoff voltage law. In summation notation, we can write Vn, where n varies from 1 to capital N, is equal to 0. So, these are the KVL and KCL for solving a circuit. Now, the question is, why do we need these KVLs and KCLs? So, answer to this is Ohm's law by itself is not sufficient to analyze complete circuits. When this is coupled with KVL or KCL, we have sufficient equations to solve the circuit. Here this KCL or Kirchhoff current law is based on the law of conservation of charge. On the other hand, the KVL, which is Kirchhoff's voltage law, is based on the conservation of energy. And the KVL KCL can be applied to AC circuits as well. Provided we use phasor sums. Instead of algebraic sum. So, why do we need KVL and KCL separately? So, the answer is Ohm's law is not sufficient to analyze complete circuit. Ohm's law specifies only for that particular element based on the voltage we apply, how much is the current in that element only. But when this element is connected along with hundreds of other elements, what is going to be the voltage across this and what is the current, that is not straightforward to solve using Ohm's law. So, we need KVL and KCL. KCL is nothing but the law of conservation of charge and KVL is the law of conservation of energy. The KVL, KCL, these laws, they can be applied to AC circuits as well, where we apply a AC signal instead of a DC signal. However, we need to make small changes. Instead of the algebraic sum what we just saw, that algebraic sum is 0, instead of algebraic sum we need to have phasor sums, where in phasors we have a magnitude as well as an angle also associated with that particular parameter. So, KVL, KCL we can apply in AC circuits as well. So, next we see how do we solve the circuit using KVL, KCL and the Ohm's law. So this is called mesh analysis. So for this, first we need to specify some definitions. So first one is the loop. So what is a loop? Then we have something called mesh. We will see something called mesh analysis. And then we will see something called planar circuits and non-planar circuits. So the first thing is loop. So this is nothing but a closed path with no node passed more than once. Mesh is a loop that does not contain any other loop within it. So a mesh is a loop itself, but that does not contain any other loop inside it. Mesh analysis is only applicable to circuits that is linear. So this mesh analysis is only applicable to circuits that are linear. And what are linear circuits and non-linear circuit? A linear circuit or a planar circuit planar circuit is one that can be drawn in a plane with no branch crossing one another. and a non-planar circuit is one that can be drawn in a plane with branches crossing one another. So, in the mesh analysis, where we learn how to solve a circuit, we first need to know these definitions. So, what is a loop? The loop is a closed path in a circuit where we go from one node to another node and we make a complete cycle, but we do not pass through the same node more than once. So, we consider each node only one at a time. So, this is called the loop in the circuit, and mesh is nothing but a loop which does not contain another loop inside it. So, it should not have any other sub loop inside a loop. So, that loop is called a mesh, and we do mesh analysis to solve the circuits. The mesh analysis is applicable to circuits that are planar. The planar circuits are those which we can put on a plane without any branches overlapping each other. So, we can put them on a single plane. Non-planar circuits are those circuits where branches are connected in such a way we cannot put them on a single plane. Always there is a branch overlapping the another branch. So, these are planar and non-planar circuits. So, let us see some example how do we solve a circuit using KVL, KCL and mesh analysis. So, let us see one example. So, here we see a circuit which is containing R1, R2, R3, these are three resistances, and we have two voltage sources which are V1 and V2. So, now we want to solve this circuit and find out all the node voltages and the branch currents inside this circuit. So, how do we solve this circuit using KVL and KCL? So, first we apply KVL in mesh 1, which is this mesh, and this is the second mesh. So, we apply KVL in mesh 1, we write minus V1 plus I1 R1 plus I3 into R3 is equal to 0. This is one equation we can write, and we apply KCL at node B. We can write minus I1 plus I2 and plus I3 is equal to 0. It means I3 is equal to I1 minus I2. We can put this into, let's say this is equation 1 and this is equation 2. We can put the value of I3 from equation 2 to 1. So we can come up with we can write V1 is equal to R1 plus R3 into I1 minus R3 into I2. So this is one equation we get from mesh 1. Similarly, we apply KVL in mesh 2. You can write here R2 into I2 plus V2 minus R3 into I3. This should be equal to 0, which is the algebraic sum of all voltages. We can replace I3 again with from the earlier equation. So we can write R2 into I2 plus V2 minus R3. I3 we can replace as I1 minus I2 equal to 0. This gives us one more equation, which is V2 is equal to minus R3 into I3 plus R1 plus R2 into I2. So this is one more equation we get from mesh 2. So now these equations we generate from the mesh analysis of this given circuit. We assume two currents which are flowing in two meshes, one is I1, one is I2, and we write KVL and KCL for these currents as minus V1 plus I1 R1 plus I3 into R3 equal to 0, and KCL is I3 equal to I1 minus I2, which is at node B. So this gives us our first equation where we have two unknowns I1 and I2. So this is one equation. For another equation, we write mesh analysis for the mesh 2, which gives us one more equation V2 equal to minus R3 I3 plus R1 plus R2 into I2. So now if we see closely, R1, R2, R3 all are known to us from the circuit. V1, V2 is also known to us, which is the given value. It may be 1 volt or 2 volt depending upon the circuit. So the only unknown in these two equations are I1 and I2. So we have two unknowns and two equations. We can easily solve it to get the values of I1 and I2. And once we know I1 and I2, we can calculate the individual voltages in each of the nodes. For example, the voltage across R1 will be V1 equal to I1 into R1. R1 is known and I1 will also be known from these equations. So we can solve this circuit from these two equations. So this is one example where we do mesh analysis to solve electrical circuits using KVL and KCL. So let's take one more example. We want to find out the mesh currents I1, I2, I3, which is the current here. This is, let's say, our mesh 1, our mesh 2 is this one, and this is our mesh 3. So, this is our mesh 1, this is our mesh 2, and this is our mesh 3. So, here we are given that we use 4 resistances 10 ohm, 12 ohm, 4 ohm and 24 ohm. These are connected in such a way with a voltage source which is 24 volt. Here battery is a voltage source, and we have a dependent voltage source here. The value of this dependent voltage source is 4 I naught, and I naught is the current flowing into this 10 ohm resistance. So, this I naught, whatever is the value of this I naught, this is actually dictating the value of the voltage which is being developed here. So, these kind of things are possible because if we remember, we have discussed the MOSFET, and MOSFET is nothing but a voltage controlled current source. It, depending upon what voltage we apply at the gate, its current changes. So, the current is dependent on the voltage. In the opposite case, we can have a device where the current is changed, and depending upon the current, the voltage across the device can be changed. So, that device can act as this kind of dependent source. So, we have this circuit now. Let us see what is the solution of this circuit using mesh analysis. So, we can write here KVL, applying KVL in mesh 1, this is our mesh 1. We can write such equations. Minus 24, this is the voltage. We come, according to the current convention, we come up with a negative sign on the battery. So, we write minus 24 plus 10 times I1 minus I2, which is nothing but I naught. So, if we see at the node A, all the sums, all the algebraic sum of the currents should be 0. So, at node A, I1 is coming and I2 and I naught both are going away. So, I1 should be equal to I2 plus I naught. So, we can write I naught as I1 minus I2. So, this is what that I naught is, and then plus 12 I1 minus I3, which is this current here. So, I1 will be flowing in this loop and I3 is flowing in the opposite direction. So, effectively I1 minus I3 multiplied by the resistance 12, this is the algebraic sum of the voltage. So, this should be equal to 0. It gives us our first equation, which is this. Again, applying KVL in mesh 2, we get this equation, and applying KVL in mesh 3, we get this equation. So, if we applying KVL in mesh 1, 2 and 3, we get all these different equations. Now, at node A, I naught is I1 minus I2, as we can see that this gives us this equation. Now, we can use Cramer's rule or some solver. We can, in fact, we have 3 equations here. So, we can easily calculate the 3 unknowns, which are I1, I2 and I3. So, based on these 3 equations, we can solve or by putting one value from one to each other. However, we can use the Cramer's rule, which is important because in our software tools, for example, SPICE, we generally use this kind of setup to solve these equations. These equations are generated from the schematic where we specify the circuit connections. Then a solver, which is for example SPICE or any numerical solver, it creates these equations from the circuit, and these equations are solved using some matrix form which is given here, and we use Cramer's rule. So, these are nothing but the parameters from I1, I2, I3 calculated from the previous equations from the last page. I11, minus 5 and minus 6 are the coefficients of I1, I2, I3 from the last equations. So, there are 3 equations here, 1, 2 and 3. This gives us I1, I2, I3 and 12. Then we calculate the first determinants, which is this value, the value of this, which is comes out to be 190. Then to calculate I1, we need to calculate del 1, which is replacing this value with the first column. So, if we see here, this whole thing is the same as delta replacing first column. So, this column we have actually replaced by the voltage sources. So, this is del 1. Similarly, we calculate del 2 and del 3, and the value of I1 is nothing but del 1, which is this one, del 1 upon del, and it comes out to be 2.25 amp. I2 is del 2 upon del, and I3 is del 3 upon del. So, this is how we solve the circuit using KVL and KCL, and in this we use mesh analysis. So, we make all possible meshes in the circuit. In this example, we have 3 meshes. So, we write 3 variables I1, I2, I3 and try to solve these variables I1, I2, I3 based on the 3 equations. So, for solving 3 variables, we need 3 equations. So, we write KVL, KCL into the circuit and solve using these equations. How do we solve this? That is different from the tool to tool. Most of the tools use this Cramer's rule to solve these values of I1, I2 and I3. So, this is how we make the circuit from the components, and we use certain rules such as KVL, KCL to solve the circuit and generate the output. So, these I1, I2, I3 are nothing but the output of the circuit. From these parameters, we can know all the terminal voltages and currents in the circuit. So, this is all for today. Thank you.